G'day girls. Alright, so this is part 1 of 2 looking at the periodic table and periodic trends. You should all be familiar with the periodic table, how it's laid out. Some of this will be revision, so let's just get straight into it. So basically the modern periodic table, all of your elements get arranged in order of increasing atomic number. The periodic table is effectively a chart that shows 118 chemical elements that we know in that order of increasing atomic number. The periodic table is broken up into a couple of parts. So we've got periods, which are the rows of the periodic table. We find that there are 7 periods. Just remember, if you think back to the way that the periodic table's set up, your lanthanide and actinide series actually fit into periods 6 and 7. All elements in the same period have the same number of electron shells. So everything in period 4 will have 4 electron shells, period 5 electron shells. And what that will look like is if you did your subshell configuration, like 4s, 5s would be your outer one. So that's how it sort of works. We normally use main shell electron configuration to determine the location though. And that's the Bohr one. Your groups, they're your vertical columns. There's 18 groups. There's 8 main groups, which are the 1 to 2, and we use Roman numerals to refer to them. Okay, but if we're just using standard numbers, it's just 1 through to 18. Elements in the same group have a few features in common, or a couple of features in common. The main two are that they've got the same number of valence electrons and that they will have similar chemical properties. There are special groups on the periodic table. There's really sort of 5-ish that you need to know about. The first one's your alkali metals. So they're your group 1 metals. All of these form ions with +1 charge, so they're going to lose 1 valence electron in a chemical reaction. We never find these in their elemental form in nature, so you're not going to go out and find a chunk of sodium or a chunk of potassium. And that's because they react really violently with water. So for instance, sodium will react with water, and what we get in this case is we get sodium hydroxide and we get hydrogen gas. Okay, obviously that's not balanced, but that's what we get. If they react with an element from group 17, okay, and we'll talk about them later, but they're your halogens. What they'll do is they'll form an ionic salt, so something like sodium will go to form sodium chloride if it reacts with chlorine, so we'll get NaCl out of that, but you might get like potassium iodide or some other form, depending on what you're reacting it with. Your alkali earth metals are group 2. They lose 2 valence electrons, so you form an ion with a charge of 2 plus. They'll also react with water, but not as violently, so you can actually find these to some extent in nature. So something like calcium hydroxide will get formed if we react calcium with hydrogen. So we'll get CaOH2. And we also get that hydrogen gas being produced with it as well. So group 1, alkali metals, alkali earth metals, group 2. Group 17, we have what are called halogens. Halogens are really important. They're your most reactive non-metals. They form ions with -1 charge. They're also able to form diatomic molecules quite regularly. So iodine, bromine, chlorine, fluorine. They all have distinct colours as well. So for instance, bromine's a brown colour when it's in solution. They react with your metals in group 1 and group 2 to form ionic salts. So something like potassium, if it reacted with chlorine, would form potassium chloride. Okay, something like magnesium, which is group 2, because it's +2, would form magnesium chloride as well, but you'd have a different ratio in there for it, so MgCl2. They also, like I said, are quite reactive. The reactivity of these decreases as you head down the group, so fluorine's your most reactive of these. The main thing that this does is if you place a more reactive halogen in with a less reactive one in solution, it will displace it. We will look at this in more depth, but if you want me to go through that, I'm happy to do so. Other groups of interest, group 8, so that's your noble gases, colourless, full valence shell, they're inert, they exist as monatomic gas, so they're happy on their own. One thing about them, as you go down the periodic table, their density will increase. And then your transition metals, they're the ones located in the D block, so between group 2 and group 13. The main one with this is that your elements can have multiple valencies, so that means that they can form cations with various charges. So something like copper can be copper plus or copper 2 plus, something like iron can be iron 2 plus or iron 3 plus. They tend to be denoted by a Roman numeral between the cation and anion to help you out. The ions of these tend to be very brightly coloured as well. So like copper, if you put it in solution, is always blue. Various iron ones will be bright yellow, like, which was the one I was thinking of? Iron nitrate. So yeah, they're quite colourful. The periodic table as well is also broken up into blocks based on that whole SP, D and F orbitals, okay? And we've sort of looked at this before, but you've got your S block here, okay, your D block in the middle, P block over to the side, and your F block down the bottom, which actually fits up into here, all right? Just also remember that we can separate our periodic table off into metals, non-metals, and metalloids. So your metals, everything to the left of metalloid staircase except for hydrogen. Non-metals to the right of it. A couple of properties of them. Metals, lustrous, so shiny. Electrical conductors, heat conductors. Ductile, so it can be stretched into a wire. Malleable, so you can hammer them into sheets. Any others that we needed from there? Don't think so. Non-metals, you're looking at the opposite. So where metals are lustrous, non-metals are dull. Where metals conduct or heat or electricity, non-metals don't, with a couple of exceptions. So for instance, graphite will conduct electricity, and that's just carbon. They also tend to be quite brittle, and they will exist in various states, so gas, liquid, or solid, whereas metals will tend to be all solids apart from mercury, which is at room temperature, a liquid. Your metalloids can have properties of metals and non-metals, so that means that when they react, they can either lose or gain electrons. And that's the basis of the periodic table.